Number of squareful arrays. Given an array A of non-negative integers, the array is squareful if for every pair of adjacent elements their sum is a perfect square. Return the number of permutations of A that are squareful. Two permutations A1 and A2 differ if only, okay, I mean, they're different, right? Okay, maybe this is a thing that we'll have to play around. I mean, these kind of math problems are always my nemesis. I would say one thing to note is that, okay, that's kind of, I was hoping that n would be bigger, but because n is 12, so okay, so I think that this is why I usually ask about what should I call it? Like looking at the ends and the constraints of the problem. So here, well, look, you're talking about permutation. The first thing that should come up to you is like n factorial for some n, just because that's the number of permutations, literally, right? Is in the name. So then when n is 12, 12 factorial is, according to my calculator, 479 million, which is way too slow, right? But it turns out that there is a symbol. Is it all every pair? There's a symbol. Symbol dynamic programming solution that this deals with. I think there's even a, yeah, I mean, I think this one I usually solve with top down, because these kind of because and it turns out to be n times 2 to the n, something like that. And the reason why and the reason why I usually, yeah, that should be okay. And the reason why, I forgot what I was going to say now. Yeah, so the dynamic programming problem will solve this in n to the n, which for 12 is, not bad. 2 to the 10 is like 1,000. So 2 to the 12 is like 4,000 times 12 is like 500,000 at most, right? I always skip the digit, so it's like 50,000, which is nothing, right? And usually I do these top down because like I recently I've been trying to do them with bottoms up dynamic programming as much as possible, but for these specific ones where the complexity is 2 times 2 to the n, where it symbols it makes where it kind of try to get like a permutation thing. I do it top down because a lot of those states are unreachable. So meaning that even though the worst case is n times 2 to the n, and you could get that easily by having, like let's say this. You may have to. Okay, so there's some edge cases, but in theory, I mean you have to do some maths, but yeah. Well, oh yeah, but sorry, I got lost in the track. But if the array is all the same numbers, then you could go to the worst case in theory very easily. But now we just have to kind of keep track a little bit. And there are a couple of ways you can take care of. So actually, that's the case that I didn't think about is that if I thought they may be really distinct or something like that. Maybe I didn't think that, but I just, excuse me, think about it. But you could actually calculate these very easily out. Well, usually if you have the mathematical background, which I don't know if it's reasonable in an interview setting per se, but you could calculate everything in n times 2 to the n, and then after that, you could, because you need to forward permutation, then it is just the number of permutation over some factorial of some numbers, the sigma of the factorial of some numbers, which is like a very combinatorial thing, which is something that is probably beyond my scope to kind of explain it. But basically, it's like, how do I want to even do a TLDR on it? Let's say you have like A, B, 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 C, C, and then you're trying to find the number of distinct permutations, then it's just, well, in this case, this is not 6, 7, 8, 9. Wait, is this 9 or Yeah, 9 characters. So obviously there's 9 permutation, but the distinct permutation is just 9 factorial over 4 factorial. To be clear, 4 factorial, 3 factorial, 2 factorial, right? And that's just equal to calculator ing right now. To 1260 instead, right? So these are, so that's like a combinatorical thing. So I really recommend if you have trouble with this, you just have to Wikipedia it or something like that, or like I think probably probability theory or something like that, where they go over how to count these things, some kind of textbook. So, but yes, but that's kind of the strategy that I'm going to be talking, or that's how I'm going to attack this problem. Yeah, cool. So, okay. And one thing to know for this problem is that you could define each state as just the last number and all the digits that you've used, or not, I say digits, but numbers that you've used, right? So yeah, cool. And usually I would say I like to sort these things, but I think in this case it actually doesn't really matter. So I don't, because you need to test in every order anyway, so you don't really need to sort. But yeah, I call these Go. Maybe Go is a terrible name for dynamic programming stuff, but you have the latest index and then the bit mask, right? Okay, so now we just go result is equal to go of from 0 and 0, and then that's your result. And then now we have to kind of, well, later we'll do the factorial thing that we're talking about, but okay. So what is your base cases? Your base case is if mask is equal to, okay, let's set n is equal to len of a, and then full mask. You don't actually need to do this. You can calculate it, but I'm just trying to be slightly whatever. Equals full mask. Then we turn 1 because you use everything successfully. Yeah, because that counts as one full permutation, that where everything is true. And then otherwise, yeah, otherwise you keep a track of the count and then return count at the end. You have to cache this, of course. So I'm just going to put a cache thing. Sometimes I rewrite this using array notations. But I think in Python it doesn't really matter that much. In this case, also n times 2 to the n is, as we said, like 50,000. So I'm not going to worry about certain performance optimizations that I don't need to do quite yet. Yeah, here. So now, what do you do, right? Also, let's start with. I have to kick this off real quick. So actually, let's because 0 means something in overloaded sense. So let's actually for each element in the list for x, for I x in enumerate a. Let's do that, and then let's yeah, I for the index that we're using, and then the mask is just 1 to the thing to the I. And then now we just go through it again, which is ix in enumerate a. Say if mask and 1 sub I is equal to 0. And also one thing I would say is if you're if what I'm doing right now confuse you with respect to bit masks, what I'm doing is I mean, there are further studies that I could talk about maybe in a little bit, but what I'm doing is that you look at a set of numbers, say, well, you know, I mean, set of letters, say even A, B, C, D, E. So this is 5 thingies, right? So we want to calculate what's, you know, without worrying about ordering, just like the set of them, So you could represent this as a binary number, which means 10110. This means that A, C, D, because these are the ones and so forth. And then just take another case, like here, I don't know, I'm just generating randomly, just C, E, so forth. So basically what I'm doing is just marking to see what I'm used, and then and this bit mask allows me to check, like, okay, did I use the number in the in the uh, in the position I? And if that's the case, or if we haven't used it, then we will use it. That's what I'm doing here. And then now count is equal plus is equal to go of I, and then mask or once by. This is not right, by the way. So don't. But it's mostly right. So this is unused, but you have to check that the thing where the array is squareful of every pair adjacent is the sum is a perfect square, right? So that's a little yucky, but okay, how do you check if a number is a perfect square? So you could definitely, so I mean, you could just check it in WoW, or I'm also debating whether to just have a lookup table and whether that's faster. But I mean, maybe it doesn't really matter. Things are not that slow. But yeah, that's kind of, let's put that here, right? So now we're looking at adjacent numbers. So the previous number is just the number that's in index, and then the current number is the new I. So actually, maybe it is correct, right? So so that means a sub I plus a sub index. This is terrible naming, actually. Now that you think about it. So let's just call this next index, maybe. It's more than I usually do, but that's fine. So yeah. So now you have these two indexes, and then the sum of them is a perfect square. So let's just assign this to a variable. Let's say sum is equal to these numbers. Is it a perfect square? Okay. If int of s 0.5 times 2 is equal to s, then we do recursion. Don't feel great about it. Maybe I would tend to 1e9 is what, a billion? So that's 1e4 to the 5th for the square root of that. What is that? That's 31,000. Yeah, okay, let's just do that then. Which is, so now I'm going to have a square lookup table, or set, let's just do, where just for I in range of, what is it, square root of 1 billion, which it's going to be less than 2 to the 16, because 2 to the 16 square is 2 to the 32. So yeah, let's do that. 2 to the 16 minus 1. I mean, it's not going to be that big, because I think it's just actually 32k, where this is like 65k. Would I get negative numbers? No, not in Python anyway, so it's fine. Because you could just use longs, domain performance split. Anyway, actually, I guess I could be a cool kid and try to do something like that. Right? And then now, okay. Now if s, the sum is in square, then we do this recursion. And then that's pretty much it. So this is going to be the wrong answer, but I just want to see if it gives me something reasonable. Just to kind of like compile errors and stuff like that, which, yeah. Oh, guys, use result. Huh. Oh, because I think I changed it on how I handled it. That's fine. Oh no. Oh, I don't know why I did it this way. I meant to return it. Okay. So okay. So I mean, I think we have a rough thing that's right. I mean, this is going to be one for this case because what we talked about with overlapping things. If I just look at this, it should give me, I want to say 3 factorial, which is 6. So if we give us the expected wrong answer, then I'll be happy. Yeah, 6. So, okay. So, yeah. And I'm going to just play a big example just for funsies. Actually, let's just do it all the same because I don't think I cut down anything. Was that 6? So then we could just check a little bit on the running time. And this should give me 12 factorial, which is what we said earlier, which is 479 million or something like that. Ooh. Oh, well, okay. See, this is why you test things. And the reason why this run out of time is, I mean, the algorithm is mostly right, but I forgot to cache. So, okay. So, and also checking the cache, obviously. But yeah, let's set the key as equal to, but still, you know. So if the key is in the cache, then just return cache key. This is pretty straightforward. I think I was just talking too much, to be honest, because I think this becomes second nature in how I implement these things. So like I usually just type it out as a template, but cool. This is why you test things. Okay. Again, this is what we expect the wrong answer to be, so that's good. So okay. Cool. And it also runs pretty okay. I mean, for the worst case, maybe we could do slightly better. I mean, you could probably do some pruning on it, but I'm not gonna worry about it just yet. I mean, if we get penalized for it, then I guess it is what it is, and maybe we could do some branching. I mean, branch pruning. But what we want to do is actually get the right answer first, and for that, what we're talking about is you just take the frequency and then take the factorial of it and stuff like this. And yeah, so then first I wanted to do a cache for the factorial table. So let's just do 1 times, say 12 is good enough. Maybe 13, because I always get off by once. But and then now for I in range of say 13, so 1 to 12 factorial. Let's start with 1 because, well, let's just start with 2 even. Factorial sub I is equal to is equal to factorial I minus 1 times I, right? So general dynamic programming, but I should double check because I feel like sometimes I get off by 1, but this should be okay. Right, and then now we just have to do a frequency graph thing. Oh, hey, Kimnas, how you doing? Also, thanks for the file project. Yeah. Yeah. So now, what was I gonna do? Yeah. Now we just have to take the frequency graph, and then you could do an n square maybe, but I don't even. What's it called? Counter. That's what I want to do. Collections dot count. Oops. Trying to be cool and learn something new. So I have a counter as equal to this, and then probably just go like this, right? Am I right? Let me print it out real quick to test. I'm learning just as much as y'all are, so or like in different dimensions, but you know, Python. So okay, so this is actually what we expect, so that's great. But because now what we have to do is now we just have to do for v as in values and counter dot values, because we don't even actually need the key because that gets taken care of. But we want the result is smaller than the factorial of this. Oops, that's not a okay. Right, and then I think that's all you need. Cool. Let's run it real quick, submit it real quick. I mean, and hopefully that's okay. I talked a lot. Oh, no's. That's interesting. 3 factorial over 2 factorial, so that's, okay. Eep. Okay. Let's see why that is the case. Yeah, I mean, naturally, this should only have one answer because that answer is just 18181. But That's a little odd. Let's kind of print out the result before the factorial, and then yeah, and then print out the counter. Counter should be okay though. So that's 48. Oh, is there 48 to do this? Because I like to kind of think about the sanity check. I'm using physical pencil just to kind of visualize a little bit. 48 seems a little high, but let's see. Because 18181 times 3 factorial times 2 factorial is 2 times 6 is equal to 12, but I get 48 instead, which is why the answer's off. So, double check. Maybe I misread the problem. Maybe it isn't always true. No, I thought it should be, because that gets checked earlier on already. So, oh, I don't know what this I is part of, because I refactored, quote unquote. I changed the I, but I don't know where the I is coming from. Maybe it's from one of these things, and that's probably the reason why it's giving me an issue. Not a big deal, but a little bit carelessness over there. But some of that's due to refactoring more than I feel like I got it right the first time, really. But okay, feel a little bit better about that. Not a big issue. Oh, thanks for the hosting, Okamaki. Hopefully that's what you meant. Cool. All right, let's just submit this real quick. I mean, before I say anything, okay, cool. All right. I mean, a little bit of a slow solution. So definitely there. I think the way that I did to dedupe, you could probably do it as part of the recursion. Yeah. Yeah, definitely. I mean, because the idea is that for this recursion, given the current, you could probably just add a very easy check to show that in this case, if we already use a sub next index earlier in this thing by keeping a set or something, then you don't do it again, because that's all duplicate. That's duplicate work, because that is the same number just in different position, right? But I didn't really worry about it. But I suppose we could have kind of gone a little bit better about that excuse me, for performance purposes. But overall, the same overall complexity, even if it's a general like complexity, or sorry, general like optimization that would make things really fast. Guess I forgot to leave a print statement in. But yeah, overall, really mathy problem. Not really. I mean, there's a mathy component, and if you didn't know this part, then you would have to do some coding to kind of make up for it, so that you don't get duplicate permutations. But not a big deal, to be honest. And that's not a hard thing to write. It's just so maybe that's probably the way I should have done it, to be honest, now that I think about it a little bit, because that's like 2 lines of code, because you would just have something like, like seen is equal to set, and then and a sub next index not in scene, and then that's it, literally. And then you don't have to, you could get rid of this, and as a result, for example, like this case would run 4 times faster, for example. And let's actually see if that's the case. It's 6 to 8 minutes. I mean, 4 times is always going to be a little, because you have to minus the startup cost or whatever, but it is faster. But you can also like check out the difference between. Well, I just lied to y'all actually, because we don't actually. we don't actually add this, so this would not have done anything. But like I said, there is some fluctuation in that, right? But we could play around with that for that reason, because if you look at this, because this is going to be the worst case. Ooh, what the hey? Maybe something is getting carried over. That is weird, actually. But yeah, let's say we comment this out. Oh yeah, no, that makes sense. It's just that because we didn't comment this part out, right? So of course it's gonna be. But it takes 192 seconds. But if we use this set optimization and also comment this part, okay, fine. Is there okay? There's no easy comment. Let's just if we do this, it should give you the answer. Knock on wood. Otherwise, I look like silly. Uh, I think I don't check it on the last one. Sorry, I don't check. I have to do a similar scene thing here, and I don't. That's why. Because did this 12 times. But I forgot what I was doing. Because that okay. Actually, I mean, I always submitted the other one, so I have it in the submission queue. But let's just add that real quick. If scene or if X in scene, then well, not in scene. Scene of right. So if we do something like that, yeah. So it's 68 millisecond versus the other case where, and this is probably going to be the worst case, at least for my particular code. And maybe it's a little slower because I didn't take out these things, but it went from 68 millisecond to so yeah, 4 times slower, and so a lot of it is like the startup cost of running things. So like the second kicker is probably gonna be slow, faster or something like that, or the constant costs are lower. But yeah, so that's kind of this problem, overall dynamic programming, and it's something that I see very commonly in competitive program. The idea of going from n factorial to the n times 2 to the n. But I would say I don't think I've ever heard something similar in what you call it in an interview. So I don't know if I mean, dynamic programming is there are many different types of dynamic programming. And I think the types of dynamic programming I've seen are more what I call stateful with respect to the prefix and sometimes subsequence, but not like these kind of dynamic programming states with kind of 2 to the n type thing, which is a little bit complicated. So I wouldn't expect it unless you're really, really good at dynamic programming. I wouldn't, unless you're already like really familiar with other parts of dynamic programming. I wouldn't worry about this just yet because you want to study or work on things that are more common before you kind of do the harder stuff per se. So that's what I would say. But overall, but once you get to that point where you're starting to get comfortable with O of n type dynamic programming, where you just take the prefix and then you do something in a linear fashion, and sometimes O of n square dynamic programming, where you have a grid and then you sometimes fill it out. Though I guess that's linear, not really the same. But also like you have some subsequence type thing, so that's n squared, sometimes n cubed, depending on how you do it, right? And so those are the two dynamic programming problems that I would recommend people to study and get familiar with if they really want to go into dynamic programming. But yeah, what's up, Kamnas? So yeah, the question is there any book videos solely dedicated to DP? So the videos that I usually recommend for dynamic programming is the one on by Professor Domain, maybe butchering his name. Sorry about that. But yeah, you type it. But he has a series on YouTube I mean, he has was it MIT OCW like open courseware on algorithms, and they're really good and very solid in general. Um, at least for me, like I feel like it's pretty good. But particularly to dynamic programming, because that's the part that I was really kind of looking into at some point. This is a freshener, refreshener, and I definitely recommend it. Yeah, I definitely should check it out. And Eric though is very good for dynamic programming. I mean, he's very good at everything. So, so not that surprised that he has a good video, but I haven't seen it yet. Maybe I should to improve my dynamic programming. But I think, yeah, but I would also say that like I would focus on getting good at the fundamentals of dynamic programming, and I think the MIT course works on the fundamental part quite a bit, quite a bit more in general. Because I mean, this is not a negative comment on Eric though. I just like I think he does stuff that's more focused on competitive programming. So I don't know how the context. So I'm just speaking from what I know. Cool. But yeah, overall, this problem I wouldn't expect on an interview, and if you do get in an interview, I mean, sometimes you just be a little sad and move on, as I usually say. Sometimes you just get problems that are just like, well, this is not going to be a happy day, but you gotta figure out what you need to do. But yeah, that's cool. That's all I have for this problem.